Okay, students, let's start. This is the week 5 content, assignment of week 5 content. In this week, we will discuss 6 questions, and in this live session, we will discuss questions related to the some impulsive forces, says the step force, step rising, rectangular pulse, and different many questions, Duhamel integrals. So we will discuss different type of questions in this session. So let me go to the questions. First question in this, we have a question related to the step force. Like, what is the response of an undamped STF system corresponding to a step force? Like, you have to choose which is the option correct, like related to the, like the which option is correct from these all fours. Like, a step force is there, so your PT or P tau is equal to P naught, P naught. So you have to find out which option is correct. So do you know the Duhamel integral? Like, by Duhamel integral we can directly solve this question, or you can easily solve this question by knowing the direct equation m u double dot plus ku is equal to p naught. Is this, by this formula you can get the solution also, but for the simplicity we have another way to solve the this form of the equation, or this form of the this form of the loading. So for this we are use the Duhamel integrals. So do you know what is the equation of the Duhamel integrals for the undamped STF system? So for the undamped STF system, ut is equal to 1 by m omega n integral of p tau sine omega n t minus tau d tau. Okay, if we put p tau, like p tau, what is a p tau? P tau is a p naught over, if you put the p tau value as a p naught and then do the integral. If you take the p naught as outside, and then inside that is remain the sine omega and t minus t tau, and if you integral with respect to tau, so that will be p naught by m omega n minus, like the integral of the sine, what is the minus cos omega n t minus tau, and this term is it's contain minus, so that minus is come here, so that minus minus cancelled out. Okay, and then put the limits, and we go to the final solution. Ut is equal to p naught by k 1 minus cos omega n t. So which option is correct? I think option A is correct option. Okay, so this is the question related to the step force. Now we are moving the another question which are related to, like the, like you have different impulse, like some triangle impulse, or some rectangle impulse, or some say sine impulse. So if the pulse duration td, let us say the pulse duration is td, is much shorter than the natural period tn, like td is much shorter than tn for both the cases. So what parameter control the maximum deformance of the undamped STF system? Like, for the simplicity, let us say if your td by tn is less than 1 by 4, less than 1 by 4, then your pulse area is most effective. Shape doesn't effective what is your shape, triangle, rectangle, or sinusoidal, but you have the area, then area will affect your pulse area, like the response. Says like td by tn is less than 1 by 4, so the response is independent of the shape. Okay, if that independent of the shape, so the response is given by, as you will have, if you have gone through the lectures on the nptl from the week 5, you have seen, like the response for the impulse is given as ut is equal to I by m omega n into sine omega n t. Okay, so the maximum deformation should be essentially controlled by the pulse area, so the option is B option is correct. Is there any doubt in this question? Anyone? Anyone is there? Am I audible? Anyone is there? Am I audible? Meena, can you hear me? Okay, if there is no question, then let us move to the another question. Which question is the what is the Duhamel integral for an undamped S-chip system corresponding to a ramp force? Like if you have given a ramp force, which rising time is the TR up to TR, this is the rising time. So the which expression define your response for a ramp force? Can anyone tell me which option is correct? Anyone? Okay, let us discuss. So what is your Duhamel integral actually, which we have discussed in our first question also. The undamped system, the Duhamel integral is given as a ut is equal to 1 over m omega n integral 0 to 2 t p tau sine omega n t minus tau d tau. So can you tell me what is the equation of this rising force? Anyone has any idea about like the equation of this line? Like let us say I want to find my point, like t is here, at what point what would be the my value of the force. So it first, like the slope of this equation is the p naught divided by tr. So at this point, like let us say it is t or some tau, so that is the value. So my pt would be p naught by tr into t. So same for p tau, that would become p naught by tr into tau. Okay, so if I will put this equation here in place of p tau, so this is a simplified, like my equation is p tau is equal to p naught by tr into tau. So my ut would become as a p naught by tr tau sine omega and t minus tau d tau. Okay, so which option is correct? Option b is correct, this option. Okay, so these three questions are the multiple choice questions, or like these are the some you have to we want to give. I want to give you some like the introductory part, like how like the related to the Duhamel integral. So now we are moving to the long problem. In this problem, like the statement of the problem is the use the Duhamel integrals to determine the response of a undamped STF system to a blast loading specified by the triangular pulse. Until like till now we have solved question related to the step force and like the step rising force. Now we have a question related to the triangular pulse. So for triangular pulse, we have to find out what is the expression of the response if my t is less than td and if my t is greater than td and the system is initially at the rest. Okay, and the part b is that we have to find out the maximum response for both the cases, t is less than td and t is greater than td. Can you tell me what is the meaning if here t is less than td and t is greater than td? Anyone? Like if t is less than td, meaning like meaning it is your force vibration phase in which your force is acting, and for t is greater than td, it is a free vibration phase, like the phase after the loading has passed and the response of your system. So in the part B, we have to find out the maximum response. And in the part C, we have to use the maximum response from the part B and find out the maximum blast force, P naught. We have to find out the P naught that can be suited to if the displacement is limited to 5m. Okay, so now let us go to one by one. So in the first part, part A, the loading of the equation, like you have given the this, this is your P naught, this is your TD. So what would be the equation of this? You can calculate easily, like the equation of this line, P naught by T into T, like TD, and that is the, like the your initially our abscissa is P naught. So that would be the P naught minus. So that is the equation, like the loading pulse for if your T is less than TD, and it is 0 if it is T is greater than TD. Okay. So first case, if T is less than TD, if your T is less than TD, so what is your Duhamel integral? Ut is equal to 1 over m omega n integral 0 to t p tau sine omega n t minus tau. So simply for the first case, put your pt value here in the p tau. Okay. If you put the p tau value, and what will become your equation? This p naught minus p naught td into tau is here in place of the p tau. Now we have to do the rearrange the equation, and we have to solve the integral. Now if I rearrange the terms, I go, like I taken the p naught outside, okay, and rearrange the terms, like first term is the sine omega and t minus t tau, and the second term is the t over td sine omega t minus t tau. If I integral this, I got this value. I got this integral, like integral of this sine omega t. What is your integral? Cos omega t, and that is also minus. Like if you say like the integral of this, so that would be the minus, and here also minus. So that minus minus will be cancelled out. So that would become plus. So I haven't written the minus here, minus, and this is the part. This is your integral of the part-wise integral. So if you do the integral of this, you will find that expression, and the put your limits from 0 to t. If I put my limits, so I will get this result. Ut is equal to p naught by m omega n square 1 minus cos omega n t minus t over td plus sin omega t divided by omega n td. So I can write this term as a k. This is my k, p naught by k. Again rearranging the terms. So again, after rearranging the terms, my final solution ut is p naught by k 1 minus cos omega n t minus t over td plus sin omega n t divided by omega n td. So this is the response when my t is less than or equal to td. Now I have to find out the response when my t is greater than td. So this is the case of free vibration. That was the case for the force vibration. Now this is the case for the free vibration. Okay. So in this case, p tau is 0, pt is 0, means p tau is also 0. So this is the first, like the free vibration case. So do you know what is our equation of the free vibration? Free vibration equation is the ut is equal to a cos omega t plus b sine omega t. Okay. Also if I have the value of, like at the time lag after td, like that is the response after the td, so that response ut would be a cos omega n t minus td plus b sine omega n t minus td. That is the maida. That is my response for this case. And here my free condition a, what would be the a? A would be utd, and b would be u dot td divided by omega n. That initially, as you know, like we have solved this kind of equation in our first or second BE. So by equation, first we have to find out what is my UTD and what is my U dot TD. Okay, so my UTD, like I have to put simply TD in place of T. I have to put the TD in this equation. So that is coming out to be P naught by K 1 minus cos omega n TD minus TD over TD sin omega n TD divided by omega n TD. And if I solve, like this will be cancelled out to each other, and that only this remains. Now I have to find what is my u dot td. So first I have to find out the u dot t. So that is my u dot t, that is my u dot t. And now I have to put, like I have simple derivative with respect to t, so this becomes this, and I have to simply replace t as a td, so this becomes my u dot td. Okay, so now the response is solution of the free vibration. So the response is become as ut is utd cos omega and td, cos omega and t minus td, u dot td divided by omega n sin omega and t minus td. So now simply I have to put this equation at the place of utd, at the place of u dot td I have to put these terms. Okay, and after putting these terms and rearranging the terms, like here I am not discussing the rearranging of the terms. So if I rearrange the terms, my final solution is comes out to be this one: ut is equal to p naught by k 1 over omega n td, 1 minus cos omega n td sin omega n t minus omega n td minus sin omega n td cos omega n td. So this is the response of free vibration when my t is greater than or equal to td. Okay, this is the my answer of the part a. Now I want to discuss the answer of the part b. Like we have to find the maximum response for force vibration phase and for the like the free vibration phase. Okay, so let's go with the one by one. So let's discuss first the for the force vibration response. Like if the t is less than td, mean the force vibration phase. So what is the response for this? Ut, we have got it. Like I have discussed in the previous slide. What is my response for the force vibration? This was the response. So if P naught by K is my UST deflection, so that is my the RD, response deformation factor. Okay, response factor. This is my RD. So my RD is 1 minus cos omega n t minus t over td plus sin omega nt divided by omega and td. Now if I want to find the maximum value of this rd, like when will be my response would be maximum? If my rd will be maximum, like ut for maximum, rd should be maximum. And for rd maximum, I have to find out drtd, rd divided by dt should be 0, and find out the what is the value of t. at, at that value of t, my rd would be the maximum. Okay, so for that I differentiate rd with respect to t. drd divided by dt is equal to 0. So drd divided dt become, if I differentiate it, 1 is 0, cos omega and t become as a omega and sin omega and t, and t over td become as a 1 over td, and the sin omega and t become as a cos omega and t divided by td. Okay, and put is equal to 0, and after putting is equal to 0, this term become as a omega and sin omega t is equal to, like taking the td as a LCM, and that is equal to 1 minus cos omega t. And if I send the td to here, that is become omega and td sin omega and t is equal to, and what is the formula of like 1 minus cos omega and t square, I can return it as a 2 sin square omega and t by 2. Okay, so if, like how, like cos theta would be 1 minus 2 sine square theta by 2. So if that is comes out to be here 2 sine square theta by 2, so that will become 1 minus cos theta, cos 2 theta, sorry, cos theta. Okay, so same thing I have used here formula. And if I replace like this sin omega and t, I can write it sin omega and t sin 2 theta. What is my sin 2 theta? Sin 2 theta is equal to 2 sin theta and cos theta. If I write it here and that is here, one sign terms will be cancelled out. Okay, so remaining term is only this one. Okay, so the omega n td is equal to tan omega n t. So what is my t value coming out to be here? Omega n t divided by 2 tan inverse omega n td. So my t value maximum here, from I get the t value is the 2 over omega n tan inverse omega n td. So that would be my t, where the my rd will be the maximum. Okay, so now I will simplify this term so that we can find out the maximum response. So for this I am using some trigonometric formulation. So like, for the trigonometric formulation, let us consider u is equal to, like, omega nt, this term I have considered as a u, and this term I have considered as a x. Okay, so this is my term here, u and x. And if I put that equation become as a u is equal to tan inverse x, and x become as a tan u. So if you know x is equal to tan u, what is the meaning? I can find out here the cos sine terms also easily. Like, this is my triangle, tan u means this is my u angle, and x, this is this, or this is unit, so that would become as a 1 plus x square. So what would be my sine u, and what would be my cos u? So sine u would become as a x over 1 plus x square, and cos u would become as a 1 over 1 plus x square. Okay, so these terms are here. So now these things we will utilize in your equation RD to maximize it. Like, how do we simplify the terms? Okay, so the rearranging the RD, like that was the my RD. So as I have considered u is equal to omega and x is like the first I have simplified this cos omega nt. I can return cos omega nt as a 2 cos square omega nt divided by 2 by 1, like this term is replaces here, and t over td is written here, like t over td is there. And if I return omega and td, I have taken outside, and I have done this as sine theta as a 2 sine theta by 2 and cos theta by 2. Okay, now I know the term, like u is equal to omega n by 2. Like, as previous slide I have taken u is equal to omega n by 2 and x is equal to omega n td. So the omega nt I have replaced with the u in this equation. Okay, and omega n td here I can also replace with the x, so I can replace it later also, that is not a bigger issue. So after replacing with this u, if I will put what is my sin u and cos u value, sin u is this and cos u is this. So what is my cos u value? 1 over square root of 1 plus x square, so that will become as a square, so that root is become 1. And sin u and cos u, these are the value of the, this is the value of sin u, this is the value of cos u. So if you rearrange the terms again, that will be cancel out, these terms will be the cancel out. And this is the t simple, t is equal to whatever I have find out t from the, like the initially I have told you, t is equal to 2 over omega n tan inverse omega n td. So I have put directly that value here, this value. Okay, so that would that value is same as here, so that is cancel out, and 2 is there. So the my response RD maximum response has become this, RD is equal to this 2 minus Tn over pi into Td. So if I want to find out the maximum response, so I will multiply ut, what is the ut maximum, ut is equal to p naught by k is my already fixed, and RD maximum. So what is my maximum value? This. Okay, now we are moving to case 2. if my T is greater than TD, which means the response is the free vibration. Okay. So for the free vibration, what is my equation? This is like, if you know, you have a equation, like let us u is equal to a sine omega t sine theta plus b cos theta. So what would be your maximum amplitude? That will be a square plus b square. Okay, so same thing I have using here. So your RD would be this, and this is your, let us suppose this is your constant a, and this is your constant as a b. Okay, so what would be your maximum? So the maximum response will be this, omega t is outside, and that will become your maximum response. Okay, so this is the part 2. Part 1 and part 2 was finished. Now we have remained with the part 3, in which we have to discuss, like using these two cases, like this case and this case, we have to find out the response. But there is a question, like if I have given a, like the triangular response, and I want to find what would it, at what value of TD by Tn or TD or T my response would be the force vibration or by the free vibration, because else I can do both the things, like I have given a time period and calculate both the response due to the free vibration, response due to the force vibration, and then find out which one is the maximum. So the maximum would be the directly given way to the response, like in. But why I should find out both the value? If I know initially that it up to this TD by Tn my response would be the free vibration or the force vibration, I will calculate directly only the that response. Okay, so I have plotted, RD is plotted with TD by Tn for both the cases, force vibration and the free vibration. So if I have plotted this response for the RD, I have find out up to TD by Tn is equal to 0.371. My response is given by the free vibration response. If my period range is falling around this, TD by Tn is less than 0.371, like TD by Tn is less than 0.371, so my response can be calculated through, maximum response can be calculated through the free vibration response. If my TD by Tn is greater than 0.371, my response would be governed by the force vibration response. Okay, so I have also written this here, like TD by Tn is this, then there to the free vibration, TD by Tn is greater than 0.37, then it would be the force vibration phase. So now by using these things, we are moving to part C, in which we have given the mass 10 raised to power 7 kg, stiffness 9 to 10 raised to power 9 kg, 9 Newton per meter, maximum displacement is given to you 5 mm, natural frequency is, can you calculate it, omega n is equal to square root of k by m, so that will be comes out to be 30 radian per second, and time period Tn comes out to be 2 pi divided by the omega n, so that is comes out to be 0.2094 second. So now can you calculate what is your Td by Tn? Sorry, case 1 TD is given to you zero point 0.4 second, so if you calculate it, TD by Tn is comes out to be 1.91. Okay, so if my TD by Tn is 1.91, that means my response is greater than 0.371, that is greater than 0.371. My response is governed by the force vibration, force phase. Okay, if that is the thing, I will, like the peak occur in the force vibration phase. So now I will use my maximum response in the force vibration phase, which was this. I have find out in the part B. RD is equal to 2 minus Tn divided by pi Td tan inverse omega n Td. I have value of Tn, I have Td, I have omega n, all the values are with me. So I can find out the RD, and my RD comes out to be 1.75 TD. Now I have given, like U maximum, it comes out to P naught by K into RD maximum. Like I have U maximum, RD maximum, K maximum. I have to simply find out the P naught. So this you can find out simple mathematical calculation. So unit is given to you 5 mm. I converted it to the meter. That is 5 into 10 raised to power minus 3 is equal to P naught by K into RD. And my K value is the 9 into 10 raised to power 9 and RD value is the 1.75. And if I will solve this equation, I find out my P naught as a 25,714.3 kilonewton. So this is the P naught value for my case 1. When TD is given to you zero point 0.4. Now the case 2 is given as TD is 0.04. If my TD is equal to 0.04, can you find out what would be my TD by Tn? So that would be TD by Tn would be the 0.191. Okay, so that is less than 0.371, means my vibration or my maximum response is governed in the free vibration phase. Okay, so what is the response, maximum response of my free vibration phase from the part B? That is this RD is equal to 1 over omega n TD square root 1 minus cos omega n TD whole square plus omega n TD minus sin omega n TD whole square. Okay, now put the value of the omega n TD, whatever value you have. If I put these values, my RD will comes out to be 0.576. Okay, now I have RD, I have U maximum, same thing apply for here, and you will get your P naught here for the second case. Okay, now you know what is the 5 mm divided by the 1000 to convert it into meter. So that comes out to P naught by K into RD. So that will become that P naught is 78,125 kilo. Okay, so this was a very long question, but it is very helpful to understood like both the phases, free vibration phase, force vibration phase. So you can actually analyze, like I have to find out the response in the which phase, like maximum, like in the free vibration or the force vibration phase. Okay, now we are going to another question, which is a very simple question actually. Like this is the impulse question and everyone can solve it easily. Like we have a question: a water tank is given to you, which mass is given you the 700,000 kilogram, and the stiffness is given to you 7,000 kilonewton per meter, and the height of the tank is given as a 45 meter, and is subjected to a dynamic loading which given to you in this figure, pt versus t. So we have to find out maximum overturning movement at the base of the tower. Okay, like you have given the loading, you have given the dynamic property or the general property of the water tank, you have to simple find out the response. So first, what is your mass is 700,000 kilogram, stiffness 7,000 into 10 raised to power 3 newton per meter. So the natural frequency would be the omega n would be the square root of k by m, that would be the 7,000 into 10 raised to power 3 divided by the 700 700,000 kilogram. So my omega is 3.16. My time period, can you calculate, like the time period is 1.986. So I have discussed a question number 2 in this session, like the if my TD by TN or the pulse duration is much shorter, then what parameter control my response, like which parameter we use our response. Like here my TD is, what is my TD is 4 into 0.05, so that is zero point 0.2 second. So here my response or the my pulse duration is very much shorter than the time period, which time period is approximately 2 seconds. So that TD by TN, if I calculate, that comes out to be zero point 0.1, which is less than 0.25. Okay, means my pulse area is not depend on the type of shape, it depend on the area of pulse. So I can calculate the diagonal the pulse. So the response is given maximum. Actually, response is given due to the impulse for the undamped system, that is the I divided by m omega n into sine omega t. That is the simple response for ut. But for maximum response, I consider it as a 1. Okay, so that become as a my maximum response is I by m omega n. So first I is the impulsive area. So what is my impulsive area? I have to find out. Like, you can use the Simpson third rule or directly calculate, like this is a triangular area, one triangular area. So that area will be the 1 by 2 into 155 into 0.05. Okay. Now this area you can calculate as a quadrature, that is 155 plus 220 divided by 2 into 0.05. This is a triangular area. This is also the quadrilateral area. In this also you can use 220 plus 65 divided by 2 into 0.05, and this is our triangular area. So that is become as a 1 by 2 65 into 0.05. Okay. So this is the, like I have writing here generally, but if you use, like I have written in the typing, like my impulsive area is comes out to be this. I is equal to 155 divided by 2 into 0.05. That is the first duration. Now that is the second, that is third, and that is fourth. And if I have calculation or calculated it, it gives me the 22 kilonewton second. So my response is given by this I divided by m omega n. So what is my I? 22 kilonewton second. So I converted it into the Newton second, multiplied with the 1000, and m is given as a 700,000 kilogram, and the my what is my natural frequency? That is given as a 3.16. Okay, so do the calculation. So my u naught is comes out to be 9.945 into 10 raised to power minus 3 meter. So if you find out the u naught, you can find out the force into the water tank, equivalent static force. Like, if like this is your water tank kind of, and this is your deflection. So what will be the force generated here? Static. That will be the, like deflection is delta, but stiffness is this. So F is equal to K into H. So your H is delta. So that is delta. So delta is given to you around 9 mm, and K is given to you 7,000 kilonewton per meter. So F into K u naught. So calculate the force. That is comes out to 69.62. So the overturning moment, how much it comes out to be? So the overturning moment is comes out to be this. Like this is your F. So and this is your F. So that will be the F into H. Okay, so that is f into h, and if you calculate this 69.62 multiplied by the 45, so that comes out to be 31 3,132 132.91 kilonewton meter. So this is my the bending moment in this case. Now we are moving to another question in which a story is single STF system shown in the figure. Like the height of the column is given to you 4 meter, and there are two columns, and they are hinged at the base. The natural period of the system is given to you 0.5 second. Each column has a moment of inertia is given to you, like the 2772 centimeter per 4 centimeter 4 power 4, and the section modulus is given to you 252 centimeter cube, and the Young modulus is given to you is equal to 210 raised to power 9 Newton per meter square, and a rectangular pulse of 20 kilonewton, like a rectangle pulse which amplitude is the 20 kilonewton here, and that is allow up to zero point 0.2 second apply to the top of the frame. So determine, we have to determine the displacement at the top of the frame and determine the maximum bending stress at the frame. So first, can you calculate what is the stiffness of the column? Anyone here? Can you tell me like what is the stiffness of the one column if the my base is hinged? Anyone? Is anyone is there? Sumed, can you hear me?
Yes, yes, I can
Sumed,
hear you.
you are not audible. You can write in the chat box if you have
Actually,
any
I am in
queries.
travel. I am in travel.
You are not audible, Sumit. If you have any doubt or anything else, you can type in the chat box. Okay. So first, like the time period is given to me zero point 0.5 second. So I have to calculate by TD by TN. Okay, if you are in travel, then okay, I will discuss the things. You can like you have to like watch, like if there are any doubt, you can text me. Okay. So first, the time period is given to me zero point 0.5 second. So the pulse duration is given to you zero point 0.2 second. So if you can, you calculate by TD by TA is zero point 0.2 divided by zero point 0.5 is equal to zero point 0.4. So if like for the rectangular pulse, when will be my RD will be maximum? There are two cases. If my TD by TN is less than zero point 0.5, if my TD by TN is greater than zero point 0.5, if my like these are the two cases for the rectangle pulse. If my TD by TN is less than 1 by 2, that is my response. RD is given to you 2 sine pi TD divided by TN. And if my TD by Tn is greater than 1 by 2, so the response is given by maximum response is 2. So here my TD by Tn is zero point 0.4. So the first case is applicable, RD. Okay. So simply for TD by Tn less than zero point 0.5, I can find out what is my RD. That is comes out to be 2 sine pi TD by Tn. And if I calculated this RD, that comes out to be 2 sine pi TD by Tn is zero point 0.4. So that RD comes out to be 1.902. Okay, now I have got my RD. So what is my maximum displacement at the top? That is a U naught divided by P naught by K into RD. P naught is given to you 20 kilonewton. What is my K? Because I have find out RD, we have to find out what is my K. So for the hinge supported, my stiffness for the one column is the 3 A by L cube. Okay, and if my column is supported is a fix, if my column is fixed, like you have given another question with the fix, only difference is my stiffness would be the 12 ei by l cube, 12 ei by l cube. So here my stiffness is the 3 I by l cube. So E is given to you 200 into 10 raised to power 9, and I is given to you 27 70 into 10 raised to power minus 8. Length, or length means the height of the column, is given to you 4 meter. So that stiffness comes out to be around 260 kilonewton per meter. This is for the single column. Like I have two columns, so the stiffness will be the multiply with the two. So that is comes out to be 520, around 520 kilonewton per meter. So if the stiffness is given to you, you can find out easily what is your displacement. Maximum deformation at P at top, that comes out to be U naught P naught by K into RD. Okay, so that is comes out to be P naught is a 20 kilonewton, so that converted into the Newton, 20 into 10 raised to power 3. K stiffness is 519750, right? This is the I have put it here stiffness, and RD. So U naught is comes out to be 73.18 mm. Now the part B is we have to find out what is the bending stress developed in the column at the top of the column. We have to find the bending stress. So for the bending stress, first we have to find out the bending moment. Like what is the bending stress? Sigma divided by m over z. So first I have to find out the m. So for like if you have gone through your like in the UG courses, like if your a beam is fixed and if it's deflected by delta, so what will be my bending moment? 6 EI delta over L square. This is for the fix. So can you tell me what is the bending moment if my one end is hinge? If my one end is hinge, okay, no problem. If my one end is hinge is settled by delta, so that my bending moment is given as 3 EI delta over L square. So this is my bending moment. Okay, if the my one end is the hinge, so 3 I delta. Here my delta is corresponding to U naught. Like here, same my this structure is displaced. So that is delta only. Same thing. So delta or U naught. So here I have written the U naught. So I find out what is my bending moment. So 3 into E is the 200 into 10 raised to power 9, and I is given to you as a 27 into 7 to 10 raised to power minus 8, and in the U naught is here is given to mm, so I converted into the meter, so that you can put it here, and the height of the column is the 4 meter, so my bending moment is comes out to be this around 76 kilonewton per meter if I divide it by the 1000. So now this is my the bending moment. So now I can simply find out what is my bending stress. So bending stress sigma is equal to m by z, and z is given to you 252 centimeter cube. So z is given to you, so you can find out our sigma. Okay, divided by the z 252. So sigma is comes out to be m divided by z. So that is comes out to enter Newton per meter square, and I convert it into the MPa divided by the 10 raised to power 6. So that is comes out around 300 MPa. So this is my bending stress. So these are the questions. 6 questions I have discussed. If any doubt in these questions, you can ask here, or any other problem up to this, like in the last problems, like any of you have any problem related to last sessions which will be discussed in the in this live session. Like I'm here up to 10 minutes also. Like if you have any doubt in any questions or questions related to assignments, you have any conceptual doubt, like not the exact doubt I can solve you, I can't solve, can't tell you, but you have any doubt related to conceptual up to week 5 content. So we have discussed six problem here. Three was the MCQ, one was the long derivation problem, in which one is also the calculation related problem, and two was the one is related to the impulsive direct impulse force, and one related to the your water tank. Sorry, related to the bending stress or some rectangular pulse. So these problems we have discussed, and if you have any doubt up to this, like uh, this is the fifth problem we have discussed. So I am here. Any doubt up to this? So is there any doubt up to this point? If you haven't any doubt, you can leave the session. I will upload the today's tutorial as well as the like the content. I will upload on the Moodle. Oh, sorry, on the Drive link, so you can access through there also. Any doubt? Okay, I am like stop the recording so that